You probably open it a dozen times a day, but have you ever really stopped to think about your refrigerator? It seems so simple, but what it's doing is kind of like everyday magic. So today, we're going to pull back the curtain and demystify exactly how it keeps your food cold.
So, let's just start with a question that seems to break the laws of physics. We all know heat flows from a hot place to a cold place, right? A hot cup of coffee always cools down. So how on earth does a refrigerator sitting right there in your warm kitchen make the space inside of it colder? It honestly feels like it's defying a fundamental law of nature.
Well, here's the secret. It's not breaking any laws at all. A refrigerator doesn't create cold. That's a huge misconception. What it really is a heat mover. Its entire job, the only thing it's designed to do, is to grab heat from inside the box and dump it out into your kitchen.
Okay, so how does it pull off this little thermal heist? Let's dive into the secret behind it all.
The most important thing to get your head around is this. Refrigeration is an active process. It's a heat pump. You know how you need a pump to move water uphill against gravity? Well, you need a refrigerator to pump heat uphill, from a cold space to a warmer one. And just like that water pump, it takes energy.
So what's actually doing all this heavy lifting? Well, the whole system depends on this one special fluid. It's called the refrigerant, and it's the hero of our story.
Now, this isn't just any old liquid. The entire trick to making a fridge work lies in this fluid's superpower. It boils at a ridiculously low temperature. And that one property is what lets it play these clever games with heat.
To really put this into perspective, just think about water. It boils at 100 degrees Celsius, right? Well, look at this. A common refrigerant, R134A, boils at minus 26 degrees Celsius. Just let that sink in for a second. At a temperature that would freeze water solid, this stuff is boiling away. This incredible property is the entire secret sauce of refrigeration.
So this special refrigerant is on a constant journey, moving through a closed loop of pipes inside your fridge. It's a 4-part journey, all designed to do one thing: pick up heat from the inside and dump it outside. And this diagram right here, this is the whole system in action. It's called the vapor compression cycle, and it's the engine that drives pretty much all modern refrigeration. You can see the 4 key stops on the journey: the evaporator, the compressor, the condenser, and the expansion device. Come on, let's follow the refrigerant's path.
Okay, so let's break down these 4 stages one by one. We've got evaporation, compression, condensation, and expansion.
All right, step 1. We start inside the fridge, in what's called the evaporator coils. The super cold, low-pressure liquid refrigerant flows in. Now, because its boiling point is so low, even the tiny bit of warmth from your leftover pizza is enough to make it boil. And when it boils, when it turns from a liquid into a gas, it absorbs a ton of heat. It's literally like a heat sponge, just soaking up all the warmth around it. And that's what makes the inside of your fridge feel cold.
Okay, next up. That refrigerant, which is now a low-pressure gas, gets sucked into the compressor. That's the part of your fridge you hear humming. And it does exactly what it sounds like. It squeezes that gas, packing the molecules super tight. This takes a lot of energy, and it dramatically jacks up the pressure and, as a result, the temperature. So now what we have is a really hot, high-pressure gas.
Now this hot gas gets pushed into the condenser coils. You know, those black coils you usually see on the back of a fridge. Because the gas is now way hotter than the air in your kitchen, heat naturally flows from the coils into the room. As the refrigerant loses all that heat, it condenses back into a liquid. We've basically just wrung out that heat sponge right into your kitchen.
And for the grand finale, this warm, high-pressure liquid gets forced through a teeny tiny nozzle. This is the expansion device. And that causes a sudden, massive drop in pressure. And when the pressure plummets, so does the temperature. All of a sudden, the refrigerant is an intensely cold, low-pressure liquid all over again, ready to flow right back into the evaporator and soak up more heat. And that cycle just repeats, over and over and over.
So, this cycle just keeps on running, keeping things cool. But how do we know if it's doing a good job? How do we measure how well it's working?
Well, engineers have a metric for that. It's called the coefficient of performance, or COP for short. Basically, it's a simple ratio. How much cooling you get out divided by how much work or energy you had to put in to get it.
You know, the easiest way to think about it is like a miles per gallon rating for your fridge or air conditioner. A higher COP means you're getting more cooling power for your buck, or for every watt of electricity you use.
It's the key number when it comes to efficiency.
And you gotta realize, this isn't just about keeping your milk from spoiling. This one simple cycle has completely reshaped the modern world.
What's so amazing is that this exact same cycle is running all around you right now. It's in your home's air conditioner, it's in your car's AC, it's in the massive systems that keep our supermarkets cold. And because this tech is everywhere, improving its efficiency, getting that COP number higher, is a huge deal for cutting down global energy use. And of course, the type of refrigerant fluid we use is critical, because some of the older ones were terrible for the ozone layer and climate change.
So, the next time you grab a cold drink from the fridge, just take a second to remember that tireless four-step journey happening inside. And it leaves us with a really important question for the future. As our world gets hotter, how can we innovate on this amazing cycle to keep ourselves cool, but do it more efficiently and more sustainably than ever before?